Okay.
Right. Yeah, so I guess I wanted to start a little bit exploring some tail recursion and like using lazy lists as sort of an alternative to tail recursion. And I found an interesting challenge and some unexpected results that I thought I would kind of share what I learned. I started with a problem. Oops, does everybody else see things okay? A fairly straightforward problem, basically just exploring the depth of a tree, which if we represent a tree, and I'm this is sort of a Clojure oriented talk, so I wrote it in Clojure, but you've got the AST is value, left node, right node. And so it's sort of an array of arrays in Clojure where you've got the first item representing the node value, the second representing the left node, I guess 0th element, first element the left, and second the right node, and then like I said, kind of recursive structure all the way down, right? So a fairly straightforward, and this is actually probably more complicated than need be because I added some helper functions to just kind of, here we just take we remove the value. We're only concerned with the actual children nodes, and here, like, okay, it's a leaf if it has no children, and branch otherwise. And then just kind of wrote a simple recursive algorithm. And if you're doing a tree depth algorithm in practice, this is probably way more than sufficient because, if you think about the number of nodes that you can represent in, like 2 to the, probably a couple thousand before your stack, 1,000 or 2 before your stack depth explodes, which is sufficient for a big tree, but it's depends, I guess, if the tree is balanced, right? If you're in a scenario where maybe the tree isn't balanced, let's say we do something where we create 5,000 nodes, but they're all in a row, like they're all sort of down the right side and the left side is empty. If we then run our straightforward recursive algorithm, we'll end up with a Stack Overflow. And so I thought initially I could solve this with a lazy list. And this seems to make sense if it's so I kind of created a little helper function in here where I start with the depth, and then I'm basically calling itself, like with the as it goes into the left node, we want to call the recursive function again, but incrementing the depth. So we start at the top, and then we say, okay, well, then the node on the left, I'm going to increment, and then I'm going to crawl down it, and I'm going to return a sequence of basically I'm just going to return a sequence of all the depths of the nodes, and then grab the max value. This seemed to work initially, but then if you change the structure so that it recurs on the left side, you end up with a Stack Overflow again. And it took me a while to figure out exactly what's going on here and why this actually blew up and how to fix it. And so let's take a step back and look at some other ways that people do tail recursion. One of them is continuation passing style. You basically say, what I'm going to do is you give me a function, and I'm going to call that function with the result of this function. And then you can usually make your algorithm recursive. So in this case, what I would do is I'm like, if the tree is a leaf node or an empty thing, right, I'm passing in identity as the initial value. So when our base case hits, we've got like if the tree is empty, it's just going to call identity with 0, we're done, and it returns. If it's a leaf node, we got 1. If it's a branch, then we do a little bit different. Instead of, we get the value of the left node, and then we call a function that then calls, like once we know the depth of the left side, then we can call this function, and then it can check the value of the right side and then compare and determine what the max value is. And it recurs that way. So once you've kind of written it in a continuation passing style, you can usually then replace your recursive call with recur. But again, this problem proves to be a little bit tricky because here we've got these anonymous functions. And if you add a call to recur, even though you're calling the same method, you're not doing it in tail position anymore. So that didn't quite work. Another common approach is a trampoline, where instead of, it's similar to the continuation passing style, but you're actually returning a function. And if you don't return a value, it calls that function. So the trampoline, similarly, what we want to do is if we know the value, we return the value, otherwise we return a function that might close over some of the initial state. But here again, we seem to be stuck with go no longer returns a value. So we don't know what the left depth is. We again have to, so this is a function. So we have to actually call the function before we can get the value in order to do the comparison. So we can kind of mix these ideas. So if we, well, a simple fix to this is just call the trampoline. But then the problem is that doesn't fix our Stack Overflow problem, because here we're still going to have, if we run the trampoline and then we call left again, it hits the left side, it calls and it runs the trampoline, and so our stack keeps exploding. So one solution is actually to mix both of those approaches. You can actually, this actually did work, where you have like a continuation passing style, but in the case where we needed to recur and we couldn't, we actually replaced that with an anonymous function that will then capture the state and return a function that then has a continuation that can pass that on to the next branch. That seems a bit complicated, but it explains, at least in part, once I understood how we could do it in a different way, I started to also understand why lazy cat wasn't actually working. And the reason is that lazy cat ultimately expands to lazy cat around the lazy sequence. And because this is a macro, it's kind of like, it's not actually going to call this yet until it actually needs a value. But when you call first, what happens, or when you actually try to pull the first value out of the sequence, it returns the concat around the lazy sequence. So this part is still lazy, but concat is not lazy. So first, I mean, concat is lazy in how it evaluates, but it's not lazy. Like this is the parameter that we're passing in. So this lazy sequence is lazy, but the concat, when it needs the value, it's going to try and it needs to, in order to find what the first element is, it's got to call it's got to evaluate the lazy sequence to get the first element with yet another concat and another concat and another concat and on and on. And so what we ended up is the stack actually gets consumed in the evaluation of pulling the first item off of the lazy sequence, because the lazy sequence is on the left, I guess, in this case. If it was on the right, like, so it worked before, because what concat does is when it was on the right is it would try and concat an empty sequence, and then the other part was a separate concat, which it would basically just do like, oh, if I have an empty sequence, I'm just going to return the right side. So it didn't need to consume any stack space in order to do that. And apparently this has been documented as a thing in Clojure. And this problem also comes up in Scala, like with things like monads and stuff like that. And so I actually, I'm just going to skip the monadic solution. But anyway, like in Scala, there's another similar thing, like with free monads and stack overflows, and how the flat maps have the same. Flat map is essentially equivalent of what we're doing here, the way that we're, and so there's sort of a known solution to this, and that's the way that you can rearrange these concats as like using the I guess monadic identities of like this, the way that things compose and rewriting it, such that whenever you see a concat of concat, you actually rewrite it so that it's concat of the first sequence and then the concat. And then it'll like, ultimately you get down to this empty sequence with everything else in the next concat, and then it doesn't end up consuming any more stack space. But the idea of comparing it to monads gave me the idea that there are a few monads that are actually already stack safe. Futures, for example, like put their work on a queue and then like basically just iterate through the queue, and therefore it kind of has that like stack safety already like handled for you. So one thing that I just thought I'd try is, what if everywhere that I wanted to recur, instead I returned a future, and then I would basically have my depth function, like anywhere that I had that recursive call before, I replaced with a future, and this actually works. And it looks almost identical to the previous one, or the initial solution that I had. But I guess there's maybe one thing that I would like in Clojure, like these futures, like a lot of people, like in Java, it's sort of considered bad practice, I guess, to have a future waiting on another future and to avoid the use of await. So I thought, what's a more Clojure-ish way to do asynchronous blocking thing? And so I tried to write it with a Go block. I've got some syntax that I didn't fix up there. But anyway, you can actually use a Go block to simulate the same thing as well. Maybe a little bit more syntax before, but it otherwise looks pretty much like the first solution as well, which I thought was kind of interesting. Another approach, like if you want to just completely change your algorithm, trees, Clojure has a great zipper structure. So here's a solution for this particular algorithm using a zipper that's more iterative. A zipper basically stores the path to a node. So I was able to kind of implement that same lazy seek idea where in this case, I'm basically just like zip next goes to the next node in a first traversal order, and then I just ask for the path to that node, count the number of nodes in the elements along the path, and then like apply max steps again on that. That's another way to solve this particular thing. It's not necessarily a general recursive solution for other problems, but like I said, I guess one of the things that I thought was interesting is that lazy sequences often can replace tail recursion, but sometimes it's not necessarily as straightforward as you might think, particularly when that function has multiple like recursive points with different states or whatever. And in exploring that, kind of led me to making a connection with the similar problem that happens with free monads, and the idea of just using a monad that is stack safe to begin with, and a future is one of those monads. So like if you running into a similar problem, like I said, lazy sequences are often great, but test it, make sure that it's recurring in the right way, that it doesn't blow your stack. And yeah, maybe you can solve it with a future.
Awesome, thank you so much. Does anyone have any questions?
Yeah, Kurt, did you look at the memory consumption of the feature itself?
No, I didn't actually. I was actually even curious, to see if it might perform better in the sense of like now you're actually able to essentially compute it in parallel. But then of course, there's the overhead of futures and stuff like that. And there's not a lot there that to make it, at least in this particular algorithm. Like I said, this is just sort of an insight in how you might solve similar things. So I don't necessarily know they'd be all that useful to performance test the particular algorithms. It's more of a toy example, but yeah, I mean, I was a little curious if the future may or may not perform better or worse. And I think, like I said, that would be very algorithm dependent. So, but it's worth trying.
How unbalanced did your tree have to get in order to cause a stack overflow? I had always thought that tail recursion was absolutely the solution to stack overflow problems.
Yeah, I mean, the problem is that this particular algorithm was difficult to write tail recursively because you like needed the value from the previous execution in order to make the next step. And, you know, so that's where, you know, you could, like I said, a mixing of like trampoline and CPS kind of made it truly tail recursive, where it didn't take up any stack, or at least not, you know, like more than a frame or two. But yeah, I think the stack limit was like 1,000 or 2,000. I think it probably depended on how many. You know, like to some extent, there's a little bit overhead and like the extra calls of the few things. So in some cases, it was more or less. But yeah, I think the stack frame thing was like 1,000 or something before it blew up. Yeah. Yeah.
Okay, that makes sense. You make me want to go back to my computer science textbooks. This is way cool.
Yeah, you could, I mean, obviously another, you know, thing is just being very explicit about your stack and doing it in a, you know, a more imperative style. I think a lot of the, like, you know, if you look at a Java implementation or something like I said, they'll do a more like while loop with a stack or something like that, explicit. But even then it gets a little messy because you want the previous value. So you're pushing and popping instead, and mutating a stack along the way explicitly. And I was trying to find a more functional way to do it. And that's where the trampolines and CPS, but, you know, like I said, it kind of, it felt messier than I expected. I thought it would be a little simpler.
This was a neat talk, thanks.
This is an awesome talk.